Welcome to a read along with Dr. Powell in the book Discrete Perspectives in Mathematics. We are currently in subsection 3.2.1 toward the end of this subsection, where we're looking at the idea of additive partitions and how to count them. If if we have a positive integer such as 5, an additive partition of it are um, a list of numbers of positive integers less than 5, such that when we add them together, we get 5. Notice we can use ones, we can use twos, we can even use threes and fours, and even just 5 itself to do so. Now, we want to say when two things are the same. So two partitions. So this partition and this partition we're going to count as the same partition. So basically, if we just kind of put the ones and then the twos and the threes, or however we do it, just kind of list them out every time in that or in order, so that we can actually put in the less than or equal symbol in the wherever we put pluses, and that would be a true statement. Then we can kind of organize our partitions a little better if we kind of make that characterization, and it'll help us a little better when we start counting, because we don't want to count this and then that or something like that. So let's think about how we want to count and how we want to form committees that'll actually help us count the distinct partitions. So as we were noticing in what a partition is and how we want to distinctly count it, we can think of ones, twos, threes, fours, five. And we're going to be pulling from these different categories, or we could even say these categories are committees. And you see this 1 plus 1 plus 1. We're pulling 3 ones from the 1 committee, right? But we're going to say there's only one way of pulling 3 ones. That's so that we don't like count like intermingling ones with ones or permuting or something like that. So we're going to take out any kind of counting possibility of ambiguity or anything at all by doing that, by forming our committees in a certain way and the different options that we can have. So for instance, committee 1 will say that every option of taking like a 1 plus 1 plus 1 or 1 plus 1 or 1 or just taking nothing from this committee, there's going to be one way of doing each thing. So that's good. So we just kind of set that up right away. And this similarly for 2, we can pull 0, then 2, 2 plus 2, 2 plus 2 plus 2, each just one way of doing that. Now, what are we looking for in the end? We're looking for things adding up to 5. So, and these are like frequencies or number of ways. So number of ways or frequency or what that would correspond to coefficient. So these guys right here, maybe they'll correspond to lengths or exponents. But that makes sense because we're adding exponents together to come to, and then we're adding these things together to come to 5. So we want to add these things to come to 5. So add exponents to come to 5. Oh, so these should be the exponents or the different lengths here. So if we look at our committees, they should look something like this. Committee 1, notice you have a 0, then a 1, 1 plus 1, 1 plus 1 plus 1. So look at these lengths. See, 0, 1, 2 is like 1 plus 1. 3 is like 1 plus 1 plus 1. 4 is like 1 plus 1 plus 1 plus 1, and so forth. So we get committee 1. Committee 2 will look a little different. Notice we have 0, then 2, then 4 for 2 plus 2, and 6, and so forth. But if we're just working mod x to the 5th, though, we can cut out the 2 plus 2 plus 2 because that's a little high. That's higher than x to the 4th. So we can just do this. Committee 3, if we work that out, we're just going to have a 3 because we can't do 3 plus 3. That's too big. And then same for 4, just x to the 4th and x to the 0, x to the 5th, and x to the 0. So we get our committees just like this. Then we can multiply these together. So let's kind of talk about this multiplication. So committee 1 looks like this with lots of ones. So let's suppose we want to multiply this committee or this polynomial, and it looks like in this calculation, we actually did some multiplication before. Okay, so maybe we multiply these guys together and let's see, is that what we do? Yes. So the last two polynomials, these two, we can multiply these out. Notice x fourth and x times x to the fifth goes away. We can ignore that. So we can just have to focus on x to the fourth times x to the 0, x to the 0 times x to the fifth. So that's just x to the fourth plus x to the fifth. And then this is just a 1 and times a 1, because that's what x to the 0 is. So we get 1 plus x to the fourth plus x to the fifth. So that's what we get by multiplying those guys together. Okay. And then over here, we have, okay, so then if we multiply this to community 3's polynomial, 1 plus x cubed, we end up getting this right here. It makes sense. So we have 1 plus x cubed and we multiply it to this guy. So that's like multiplying 1 to all that and multiplying x cubed to all that. Now, if you multiply 1 to all that, it's just that. X cubed to all that, it shifts that up. So x cubed, x to the 7th. Oh my goodness, we could just ignore all of that, right? Yeah. So basically, it's just itself added with an x cubed in it. So that's nice. So there'd be like a 1, 0, 0, 1, 1, 1. Actually, just we don't even go to the x to the fifth. Oh, we do want to go up to x to the fifth, right? Because we want to go up that high. Okay, so we want to go up. We can go up to x to the fifth, but we don't want to go up x to 6 or beyond because we're looking at 5. 5 is our target in this case. So we have 1. So we have a. So we're looking at this one. 1, 0, 0, 1, 1, 1. Okay, that would come from here. Now, what about this guy? What's that? Well, that we just basically just rewrite this out with the coefficients. See, a 1, 0, 1, 0, 1, and a 0. That's where this comes from. So we didn't really technically need to write that 0 out, but I guess it's written there. So, so if we multiply these last two polynomials together, all right, so let's do that. We're going to multiply these last two polynomials. So we have, okay, so we have this one, all right, 0. Okay, then we keep on shifting it. So we take, I guess we take this guy right here and we just take there, just shifting it over as we look at these. And then we just list out 1s and 0, 0s, 1, 1, 1. So just like we have a 1, 0, 0, 1, 1, 1, multiply, and then we add. And then we get this right here. Okay. So we have this guy, which is the last two, times the first one. Okay, now in this one, looks like we have, so the way we've written out this time is we have the one, it really doesn't matter, with multiplication is commutative, so it doesn't matter which order you do this in. So here we have the ones listed out this way. Okay, so basically we're just taking shifts of this over and then just adding down. And we really only need to add in this column where we have x to the fifth. And so, which we get as 7. Okay, so there's only 7 added partitions. In fact, this is all of them. Notice we could have done this by hand, but this technique at least kind of gives us a flavor for how this could be used in other situations where maybe we can't just tabulate and list it all out just like that. Anyhow, this concludes the end of this little subsection 3.2.1, discussing additive partitions. Thanks for watching.